Section 5 of Familiar Letters on Chemistry. This is a LibriVox recording. All the LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Familiar Letters on Chemistry by Justus Liebig. Letter 5. My dear Sir, until very recently it was supposed that the physical qualities of bodies, i.e. hardness, colour, density, transparency, etc., and still more their chemical properties, must depend upon the nature of their elements, or upon their composition. It was tacitly received as a principle that two bodies containing the same elements in the same proportion must of necessity possess the same properties. We could not imagine an exact identity of composition giving rise to two bodies entirely different in their sensible appearance and chemical relations. The most ingenious philosophers entertained the opinion that chemical combination is an interpenetration of the particles of different kinds of matter, and that all matter is susceptible of infinite division. This has proved to be altogether a mistake. If matter were infinitely divisible in this sense, its particles must be imponderable, and a million of such molecules could not weigh more than an infinitely small one. But the particles of that imponderable matter, which, striking upon the retina, give us the sensation of light, are not, in a mathematical sense, infinitely small. Interpenetration of elements, in the production of a chemical compound, supposes two distinct bodies, A and B, to occupy one and the same space at the same time. If this were so, different properties could not consist with an equal and identical composition. That hypothesis, however, has shared the fate of innumerable imaginative explanations of natural phenomena in which our predecessors indulged. They have now no advocate. The force of truth dependent upon observation is irresistible. A great many substances have been discovered amongst organic bodies composed of the same elements in the same relative proportions, and yet exhibiting physical and chemical properties perfectly distinct one from another. To such substances the term isomeric, from iso, equal, and meros, part, is applied. A great class of bodies known as the volatile oils, oil of turpentine, essence of lemons, oil of balsam, of copaiba, oil of rosemary, oil of juniper, and many others, differing widely from each other in their odour, in their medicinal effects, in their boiling point, in their specific gravity, etc., are exactly identical in composition. They contain the same elements, carbon and hydrogen, in the same proportions. How admirably simple does the chemistry of organic nature present itself to us from this point of view! An extraordinary variety of compound bodies produced with equal weights of two elements, and how wide their dissimilarity! The crystallized part of the oil of roses, the delicious fragrance of which is so well known, a solid at ordinary temperatures, although readily volatile, is a compound body containing exactly the same elements, and in the same proportions, as the gas we employ for lighting our streets; and, in short, the same elements, in the same relative quantities, are found in a dozen other compounds, all differing essentially in their physical and chemical properties. These remarkable truths, so highly important in their applications, were not received and admitted as sufficiently established without abundant proofs. Many examples have long been known where the analysis of two different bodies gave the same composition, but such cases were regarded as doubtful. At any rate, they were isolated observations, homeless in the realms of science, until at length examples were discovered of two or more bodies whose absolute identity of composition, with totally distinct properties, could be demonstrated in a more obvious and conclusive manner than by mere analysis. That is, they can be converted and reconverted into each other without addition and without subtraction. In cyanuric acid, hydrated cyanic acid, and cyamelide, we have three such isomeric compounds. Cyanuric acid is crystalline, soluble in water, and capable of forming salts with metallic oxides. Hydrated cyanic acid is a volatile and highly blistering fluid, which cannot be brought into contact with water without being instantaneously decomposed. Cyamelide is a white substance very like porcelain, absolutely insoluble in water. Now, if we place the first, cyanuric acid, in a vessel hermetically sealed, and apply a high degree of heat, it is converted by its influence into hydrated cyanic acid; and then, if this is kept for some time at the common temperature, it passes into cyamelide, no other element being present. And again, inversely, cyamelide can be converted into cyanuric acid and hydrated cyanic acid. We have three other bodies which pass through similar changes, in aldehyde, metaldehyde, and etaldehyde, and again, too, in urea and cyanuret of ammonia. Further, 100 parts of aldehyde hydrated butyric acid and acetic ether contain the same elements in the same proportion. Thus one substance may be converted into another without addition or subtraction, and without the participation of any foreign bodies in the change. The doctrine that matter is not infinitely divisible, but on the contrary consists of atoms incapable of further division, alone furnishes us with a satisfactory explanation of these phenomena. In chemical combinations the ultimate atoms of bodies do not penetrate each other, they are only arranged side by side in a certain order, and the properties of the compound depend entirely upon this order. If they are made to change their place, their mode of arrangement, by an impulse from without, they combine again in a different manner, and another compound is formed with totally different properties. We may suppose that one atom combines with one atom of another element to form a compound atom, while in other bodies 2 and 2, 4 and 4, 8 and 8 are united, so that in all such compounds the amount per cent of the elements is absolutely equal, and yet their physical and chemical properties must be totally different, the constitution of each atom being peculiar, in one body consisting of 2, in another of 4, in a third of 8, and in a fourth of 16 simple atoms. The discovery of these facts immediately led to many most beautiful and interesting results. They furnished us with a satisfactory explanation of observations which were before veiled in mystery, a key to many of nature's most curious recesses. Again, solid bodies, whether simple or compound, are capable of existing in two states, which are known by the terms amorphous and crystalline. When matter is passing from a gaseous or liquid state slowly into a solid, an incessant motion is observed, as if the molecules were minute magnets. They are seen to repel each other in one direction, and to attract and cohere together in another, and in the end become arranged into a regular form, which under equal circumstances is always the same for any given kind of matter, that is, crystals are formed. Time and the freedom of motion for the particles of bodies are necessary to the formation of crystals. If we force a fluid or a gas to become suddenly solid, leaving no time for its particles to arrange themselves, and to cohere in that direction in which the cohesive attraction is strongest, no crystals will be formed, but the resulting solid will have a different colour, a different degree of hardness and cohesion, and will refract light differently. In one word, will be amorphous. Thus we have cinnabar as a red and a jet black substance, sulphur a fixed and brittle body and soft, semi-transparent and ductile, glass as a milk-white opaque substance, so hard that it strikes fire with steel, and in its ordinary and well-known state. These dissimilar states and properties of the same body are occasioned in one case by a regular, in the other by an irregular arrangement of its atoms. One is crystalline, the other amorphous. Applying these facts to natural productions, we have reason to believe that clay slate and many kinds of grey-wacke are amorphous feldspar, as transition limestone is amorphous marble, basalt and lava mixtures of amorphous zeolite and augite. Anything that influences the cohesion must also in a